Our next speaker will be Jennifer Brown, who will talk about parabolic defects in coordinate theory.
Okay, cool. I'd like to again thank the organizers. This has been a lovely event, and it's very nice facilities. I appreciate this. And I would like to thank all of you for coming on a Friday to a math talk. So today I want to talk about a recent project I was working with. I think the first thing I need to say, which for some of you may be intriguing and some disappointing, is that this whole story is topological. So I'm working in what I understand is called the Kaput-Witten twist of this theory, meaning it's a topological theory. In fact, all my defects are also topological. And this is based on recent work with David Jordan, a paper that we call Parabolic Skein Modules. And I just want to let you know the original flavor of this work is this paper is 45 pages long, and I counted during math talk, and we say the word category or categories 222 times. So it's quite a mathematical piece of work, which I am trying to translate for this conference. Okay, who do we want to start? So what I want to start with is sort of let's consider this situation. I have some theory, and on surfaces, on sigma, what do I want to associate to this? Well, for me, if I have a four-dimensional theory, this means the two-dimensional part should be a category. And in particular, I want to do this category. And I assume this needs some translation for us. So what's going on here? G is I believe, my gauge group. It's a reductive group. You can think SL2, which is where most of the progress has been made. This thing here, which we'll talk about some during this talk, is what's called the character variety. And you should think that this has to do with flat connections on my surface. And this part here, which I imagine is the most mysterious, is what's called the category of quasi-coherent cheese. And to stop this from becoming a talk on algebraic geometry, I'll just give you the following facts. So if I look at this category of quasi-coherent sheaves on X, and this X is a nice sort of space we call affine, then this is going to look like modules for this thing here is the coordinate ring. My space. So when I write quasi-coherent sheaves, you can think this is mathematicians generalizing the idea of modules. And what I want to do with this, sort of the first step in this story, which was done before our work, was we want to quantize the story. Okay. And before I move on, I think this gets, maybe there's the most mysterious word in the title. For some of us, will be parabolic. For others, it will be the most familiar word. And so what's going on with this parabolic, this will show up later, is I take my group G. I will fix some parabolic subgroup, or say a Borel subgroup here. You should think upper triangular matrices. And then from there, I project down onto some maximal torus. And when mathematicians work with these parabolic groups, one thing we really like to do is pass between a theory having to do with G to a theory having to do with T. So my defects are really interfaces between different theories. Okay. Are there questions on this?
So you mean different theories with the same maximal torus, or?
Yeah, well, the maximal torus comes from G is determined by G. Yeah. So the framework you could do more generally, but that's what we're doing. Okay. So when I want to quantize something, what do I mean by quantize? Well, what I mean is I want to take this algebra and I want to give you something, which maybe I would write a little q here, that's non-commutative. So this was sort of the goal here, but because I'm working with this kind of categorical perspective, really what I want to do is apply this quantization on the level of this category and get something that's what I'll call a braided category. Just some categorical version of non-commutativity. Okay. So let's go. What's this thing? Right. So let's start off with this. CH, G of sigma. I should say, aside for mathematicians, I actually have to work with the character stack to get the right excision properties, but this is the only time I'll mention that during this talk. So this character variety, the way I like to define it is I look at group homomorphisms from the fundamental group of my theory into G, like this. So here you can already see some hint that this is quite topological. And then on this space, I have an action by G. If I have some map, I can conjugate by G. And so what I take is the GIT quotient. So right here, this is what's called the GIT quotient. Geometric, yeah. And the important part to know is that if I'm looking at functions on the GID quotient, this is going to be functions which are invariant under that action. So that's what we'll deal with. And here, this part, let me give it a name. This I'll call RG of sigma, the representation variety of sigma. Okay, so what I want to do is I want to construct functions on this. And the first idea that I may have, if I'm trying to make functions on a space of maps, there's kind of like a favorite first thing you might do, and this will be evaluation. So what this means is I take some phi, some map that goes from the fundamental group to G, and I can evaluate it at some class in the fundamental group. So this thing I'll call gamma hat. So, but this is just going from RG to G, and these functions I want them to be complex valued. So the next step that I could do is I'll take a trace. Just to say I take G, I want to take a trace. I like to take trace of matrices. So what I'll do is I'll think of it as a matrix. For mathematicians, this means I'll get some homomorphism to the invertible matrices on some vector space. And then from here, I have just some trace function. Okay, and let me just make some notation altogether. Let me just call these tau gamma v, and this goes from RG sigma to C. That.
Yes, question?
Yeah.
Isn't that RG mod G the moduli specified connections?
It is.
Then is that substantially different than quantizing, say, on a billion PF here in two dimensions?
This is the story I'm talking through right now. Yeah. Okay, so we have this story, which is familiar to many of us, and what I would call maybe a multi-theorem due to many people's work. I'll mention Procesi, Marché worked on this, Bullock has worked on it a lot, Sikora has very nice work in writing on it. Is that everyone I want to Okay. Is that if I take this set of functions, tau, gamma v, these generate this ring of functions. Which is to say, all I need to do is first evaluate and then take a trace. Okay. Can you see if I write here? Can you see if I write here? Okay. Yes, that's the worst case scenario. There's a horizon. Okay. Okay, okay. I'll move it up quickly. So now what I want to talk about is how we quantize these, in particular with a theory called skein theory. Here, skein is the English word for like a bunch of yarn that's piled up. It's not like some German mathematician's name. I will always mention this. And so the insight behind using skein theory to quantize this is that classically, what's going on when we're looking at this? The system is, well, I have my surface. And if I want to give you a function on my surface, what I have to specify is some element of the fundamental group. It's conjugation invariant. So I'm looking at this invariant subset. So I don't have to worry about base point. So I'm taking some curve on my surface, and I'm associating some representation of G. So like this. And if I give you another curve and another representation of V, these will give me another function on the surface. So the idea is to quantize this picture. And in particular, what we need is I need some way to go from the fact that my multiplication, if I think of it as just putting two curves next to each other like this, well, so here I'm maybe zoomed in around this intersection. Well, this is, the multiplication is just pointwise multiplication in C, so it's commutative, right? So I have no...
Sorry, these curves are not oriented?
They are oriented, they are oriented. Yes. Yeah, they are oriented. And later they'll be framed, and I'll never draw the framing. Okay. So what we need is some deformation of this fact. And somehow there's no height data on these things. So what we want is some way for these two to be different in a coherent way. And what gives us this is mathematically speaking the passage from a symmetric monoidal category which is a category that, like vector spaces, we have some way of combining two vector spaces with a tensor product, but sort of the order in which I combine them doesn't matter, and I can switch it very easily to what's called a braided monoidal category, where I have some, if I take V tensor W, I have some isomorphism to W tensor V. I'll call this C. But I have that C squared is not the identity in general, which it would be here. So what I want to do is I want to use the already developed descriptions of these braided ratings and categories to do this. And in fact, there's a good candidate for what to use. So what I want to use is called rep QG. And this is, by definition, representations of what's called the deformation of the universal enveloping algebra of G. Fine, maybe that's a lot of vocab words. This is an example of a quantum group. And this thing is going to look like rep G, basically, except for I'll have this extra braiding information.
Is it too early to ask what's the relation to this board?
this
Now we
board.
have an algebra there, or
Yeah, so this is the discussion of this thing. Yeah, and because I love categories, I'll actually give you the description of this thing, and then I'll use something to get back to the algebra. Okay. All right. So what I want to do is I want to take this idea that all the interesting stuff is local, and I want to make it sort of more formal. I want to say that really what I'm focusing on is these lines in here, and I'll just put them living in some thickened disk. And if you want a little more connection back to physics, these lines that I'm building, these are, in some theories, playing the role of Wilson loop operators. Or they're understood as defects in Witt and Reschke-Drive theories. Okay, but let me make my local model. And I'll call this rib subrep QG. So this is my local model for how I want these curves to work. And this is going to be a category. It'll be a linear category, so I'll be able to add morphisms. And I want, as my morphisms, I'm going to take little local drawings like this. So these are going to be, I'll just write it out and I'll say what all the words, how they go together. They'll be rep Q G colored, oriented, framed graphs in, I'll take a disk and I'll thicken it. And because that's a mouthful, I'll say, so there are going to be sums of these things. What does this look like? Well, I can take one of my graphs like this. I can have a bunch of things come up, and in here, in general, I could have some complicated graph. And all my edges, I want to have be oriented like this. They are all going to be framed. I want to draw the framing, and I want them all to be colored by objects in my category. 1, 2, 3. Yes. Okay. So I have that, and then if I have a category, it also has to have objects, right? So what are the objects of my category going to be? My objects are going to be these things. So my objects are going to be, I will take some disk, and I'll put a bunch of colored points. Each one will be labeled, and it will have a framing, which here on the surface will just look like some arrow, and it will be signed like that. And these things I'm going to call labelings. In case you're curious, my notation will be that my morphisms go up, right? So this graph here I would think of as a morphism from this configuration of points on some disks to this one. Okay.
And they cannot collide somehow?
I can have vertices. So is that what you mean by?
Yeah, yes.
Yes. Yes.
It's not clear what you mean by these plus and minuses.
Yeah, okay. So the plus and minuses are going to be associated to the orientation. So on a curve, orientation is a direction. But if I just have a point, orientation is like plus or minus. That's the data. And they can come together like this. So here, if I had V...
So only trivial.
No. I could have a gazillion. I'm just writing down one. Yeah, these are graphs, so they can have as high of valence vertices as possible. And when I say colored, what I mean here is that here I need to put some data, and this will be something from the tensor product of all the incoming edges to the tensor product of all the outgoing edges. So in this example, from here it would be something from V, which is the only incoming one, to But by far the most popular thing to work with is SL2. And then it turns out for some like rep theory reasons, you don't need vertices and you don't need orientations. But in general, you need both. Are there other questions? Okay. So
what fixes the ordering?
the framing. Yeah, framing the data framing is this. It fixes. This is a cyclic ordering, and then you need to say some category theory words to make it into a linear ordering. Okay, so here, what I've done is I've started talking about graphs, but you could imagine, even if I'm thinking of this up to isotopy, I'm going to have like a gazillion graphs to work with, right? It's way more than I want. Here, I also had this story about having some, well, here it was just curves on my surface, but I really only cared about the functions that they represent. So you could think of two of these curves representing the same actual function on my character variety. This is some equivalence relation on my curves. And here what I want is I want the analogous version of that, or general. And because we're working in this more categorical setting, the way we're going to do this is with a functor. And here's this functor. So this is a theorem by Reshetkin and Turayev, 90, which is that there exists a unique functor. So it's a functor, it has to go between categories, so this is going from QG, from this thing back to rep QG, like this. So it takes one of these graphs, or linear combinations of these graphs, and it just gives me a morphism in this category. So take something gross in here. So I have some vertices, and it just sends it to some morphism like this. And it's unique such that, so there's many conditions, which I don't think will be of interest in this audience, but say this thing turns out also to be a braided category, it needs to respect that structure. This turns out to be pivotal, has to respect that structure. So it has to respect a bunch of structures. Let's call it RT. And one of the ones that I think is sort of nice to show you that these constraints are not insane is if I have just one vertex labeled by some F here, then this has to be sent to F. So that's, for example, one of the things that you require. Which in particular, right, if this was V and this was W, that means that just a single point labeled V positively oriented has to be sent to V and W. Like this. All right, so this functor is what we're going to use to try to make our generalization of this space. And how does that going to go? What that's going to do is it's going to let us write down the following definition. The relative skein module. So how am I going to write this? I will write SK for skein, rep QG down here. And what it's going to eat is it's going to eat M, some 3 manifold, and X. This X here, this is going to be a labeling on the boundary of this thing. So I've mentioned what are our labelings for a disk right now. So if this is some genus 3 surface, this is going to be some finite collection of framed oriented points, all colored by things in my category. So one of these. And what is this? This is going to be just a vector space. And this is going to be the vector space, which is the span of these graphs. So I've made some graphs. This word here. Let's give that a name. Let's call these ribbon graphs. So it's going to be the span of such things. In M. So I'll draw a picture. I have my boundary of M. So a ribbon graph is going to be some framed oriented graph that lives in here. It can have vertices. Everything is oriented. Everything is framed. I have labels all over the place, like this. So it's going to be these things, and I require that they restrict to X on the boundary of M. So if I take one of these graphs, gamma, and I just restrict it to the boundary, well, a graph, I'm going to have it intersect the boundary. It will just be a series of points. And this I require to be X, like this. So I have this. These are going to be up to isotopy, which means they can wiggle around, but they can't pass through themselves. But this is huge. You can imagine every single graph in my three manifold. This is too big, so I need some equivalence relation on it, and this is where this functor will come in. So this functor, I know what to do if I have a thickened cylinder, or a thickened disk if I have a cylinder. I know how to evaluate, and because of this hand waving I did earlier, we have the idea that if we have two graphs that are sent to the same morphism in a category, the same intertwiner of representation, then I want it to agree. So I'll just do this locally. So anytime I can take a cylinder and embed it in my surface, so this is any thickened disk embedded in M, such that when I take my whole graph and I restrict to this disk, let's call it B for disk, when I restrict to there, I understand it as a morphism. What I want is that anytime that these two things are, let me give myself more space, this equivalence will be two of these things will be equivalent. If I restrict them, I evaluate my functor, and I get the same thing. Which is to say, inside this green cylinder, I could swap it out for anything else. So say this was equivalent to just, something else that went like that. Maybe this thing is gamma prime. It's just that I only go like this. Maybe I have some coupon here. It's like that. So I have my local relations. So here's what I'm defining. What do I want to use this for? Well, the original thing I wanted to do is come up with some quantization of this quasi-coherent sheaf business. So now I'm going to define a category. So here's my definition. I'll call it the skein category. And what you should think of it is what I'm doing now is I'm doing something that maybe you would call QQ, sub Q, CHG of sigma. So this is some quantization. I don't think people use that notation, but you can think of it that way. Okay, so it's going to be a category. What are the objects going to be? Well, my objects, I already have some objects I've been dealing with here, these labelings. So my skein category, I'll say of some fixed surface sigma, my objects are going to be labelings of sigma. So say sigma is just an annulus here. So again, something like that.
So why is this a ribbon graph? You just give that name to. Is there something
Yeah. So
called a ribbon graph, which is?
there are two things in math called ribbon graphs, which are different.
Okay, so maybe I just know of one of them.
Yeah, so you know the one on surfaces that like explain that? Yeah, so this confused me for 2 years. Those are different. These ones get called ribbon graphs because of the framing.
Yeah.
So framing is like it sweeps out a direction at each point, and so you could think of them as like embedded ribbons. So that's why. It's like really the framing, what's behind it. So it's one reason. And then the other reason is that if I just took this category and I didn't bother with any coloring here, or if I took this is like one of our favorite examples of what's called a ribbon category. So it's kind of nice to say the category of ribbon graphs is a ribbon category. So, yeah. Okay. So objects are these labelings, and morphisms so often when someone's telling you about a category, they tell you what each morphism is. I'm going to tell you what the vector space of all the morphisms are, right? So the homomorphism from X to Y, so these are both labelings. Well, I'm going to use the only vector space I've like defined in this talk so far. It's this thing, this relative skein module. And so this is going to be the skein module. The whole theory depends on this rep QG. I need a 3-manifold. I'll just thicken my surface. And I need a labeling. I have 2 labelings. And so I'll just take one and put it on the bottom, and take the other one and put it on the top. So you can think the morphisms here, each individual morphism will be some equivalence class of curves like this. So here's an example of a morphism in there. Is this up to some equivalence relation? Like that. Okay. This is my skein category. So to make this idea precise, so right now I've been talking about rep QG, but this theory I don't need it to be specifically rep QG. I could have started with a different category there. And if I take this thing, which I'll call skein cat rep QG sigma. So if I take this construction and I just plugged in rep G here, so I just color by elements of rep G. I use this equivalent functor for just rep G, not rep QG, all of that on my surface. This will give me quasi-coherent sheaves on the character variety, like that. And this sort of insight that we could construct this way, and so we can quantize it this way. This is this sort of insight, I would say, goes back to the Bouchier, Jordan. Maybe in 2018, they have a couple of papers, and some of the technical work to show that this really is true goes back to Juliet Cook's thesis in 2019. But if you are needing a non-semi-simple version, for personal reasons, for that you have to look at more recent work by me and Clara and Benjamin Ayun from 2004. Oh no. Okay.
How obvious is this equivalence for the non-deformed case? This equivalence over there, right? So OX, I inferred that it was this.
Yeah. So the way that like this equivalence here. So one, you need stackiness. This is not true for the character variety. That was a lie. And you prove it using excision. Like you prove that this quasi-coherent sheaf category satisfies the findings, excision properties of factorization homology. and then you need to prove that the skein category is factorization homology.
So it's not something as obvious as I would take a surface with some mark points and would convert it into a module.
So that is obvious. The idea that it makes sense is obvious.
Mhm.
The idea that it's true is, yeah. Yeah, I think like the original Bincy argument like was all in the derived setting.
But that's not obvious to me somehow. So the module of that algebra, right? There are no mark points on the surface involved whatsoever. If that is my whole X, this algebra, right? No mark points on the surface. And if I am taking a surface with mark points, I'm supposed to convert it to somehow module of that thing.
Yeah. So what you end up doing is you take the marked points. Each one of them is like also labeled by a representation of G, and you tensor these together, and these will give you your quasi-coherent sheaf
Okay.
on it. But then, like, if it's not affine, you have a lot of trouble. Yeah, it's a mixture of obvious and really fiddly. Yeah, and then you have to understand the Poisson structure and to really get the quantization aspect of it. Okay, but sort of as promised, this is part of a TFT. Topological field theory. In particular, some four-dimensional topological field theory. And just to say what that thing is, that's the field theory which on a surface assigns the skein category of the surface. And if I have some cobordism, so some three-dimensional manifold, and I've told you part of this boundary is incoming and part of its boundary is outgoing, well, I need to give you something for that. And what this is going to give me is, so if I have some manifold like this, you may hope that I could go from the skein category here, which is curves and graphs in this thickened surface, to the one in this thickened surface, but a three-manifold doesn't really take me a graph from here and put it there. So I'm not going to get like a functor. But what I do get, so I won't get a functor between the skein categories, but I'll get a functor involving both of them, like this, which on morphisms will take one of these labelings here, one of these labelings here, and I just send it to this relative skein module, like this. So we'll get that. And in particular, if both these things are empty, I have a closed manifold, then both of these are gonna, the skein category of an empty manifold will just have one object of a point, and its morphism space will be just whatever the base field is. So I'll draw it like that. There's one point, it's in the morphisms of the base field. One point in the morphisms of the base field. Then I go to vect. And this is going to look like more like a bimodule, or this will look just like like not a bimodule, but it will be like a vector space. So it will be a really torturous way of writing a vector space.
This is like a profunctor.
Yeah, this is a profunctor.
They're also composed like that.
Yeah, they compose like profunctors. Okay. Alright. So now what I want to do is this whole big theory, which is maybe interesting to physicists for reasons yes?
So what's known about the TFT? Is it equivalent to some other TFT that is well known?
It's what you should get from the cobordism hypothesis. Like, so it's known that it's been extended to 4 dimensions. This is like Gear, Constantino, Jumirand, Ayun did this, and it's known that it's fully extended. I mean, it's not known because extending down is very technical for the setting, but yeah, fully extended 4D TQFT.
An extended version is not constructed yet, like 4,3 TOVHs.
I think that's that's like this recent paper by Gear Constantino.
Ah, okay.
Yeah, they use like handle attachments
I see.
to find stuff, and it works for non-semi-simple settings too. But it's non-compact. Okay. Now what I want to do is say, why did I, as a mathematician who's like learned this theory, what was my project? What did we want to do with it? And that will be the rest of the talk. And in particular, our application required us to implement defects in this theory, to implement these these topological surface defects. So this is sort of step one was quantization. Step two is what's relating to this, to what's called the A polynomial, which is a knot invariant. And there's been a kind of a long-standing project in math to come up with some quantization of this. In 2011, Tudor Domofte wrote down a very beautiful quantization using hyperbolic geometry. We wanted one using skein theory. Okay, so how is this thing made? Well, if I take S1 and I embed it in, say, S3, so I fix my knot, I'll call this K, just for this data. And also I want to say, to get sort of the number of polynomials and stuff all to work out and to match with the historical story, you should just think of SL2, although it does generalize some of it. What I want to do is, given this knot and this group, I want to make a polynomial. And how is this done? Using character varieties. What I'll do is I'll take this SL2C character variety. So I take S3, and I'll remove the knot K. All right, this is what's called the knot complement. And then what is done in this construction, which is by, let me give a citation. Oh, no, okay. So this is originally back by work by Cooper, Cohen, Gillette, I've forgotten all the people, but Fuller and Cooper and Gillette are both big names, and another author who I forget, and if that was you, I'm really sorry, 94. So you take this space. What they do is they, inside there, define some subspace, which is it's all of these maps from pi1 of the knot complement to SL2C, such that if I take my knot complement, so I have my knot, and my little cartoon for the complement is going to be this. So this is S3, and this is the knot I've taken out. I have two curves in here I can define. One is, I'll write M, this is the meridian, and the other one, L, the longitude, which just follows my knot around like that. That will be L. What they do is they take this space, and they require that row of L and row of M are upper triangular. So they're in this part of this group where this lower coordinate is 0. Like this. So they take this space, and they send a map, we'll call it psi like this, to the character variety of the boundary. But here, one clever thing that they do is they simplify their lives. They send it to the C star character variety of the boundary. And what happens is that psi of the row is sent to, okay, let's think, what is this? This here are going to be maps from pi1 of the torus to C star. Pi1 of the torus is generated by this M and L. I mean, you can choose different generators, but you can choose those two. So just as two copies of Z. So if I want to tell you such a map, I just need to tell you two numbers, right? And what they do is they send this to row L11, this upper coordinate here, and row M11, that upper coordinate there. They do, and then what you get using some little bit of algebraic geometry is if you look at just functions on the image of this space, what you'll get is that this looks like functions on the whole thing. Okay, so here we agreed it's just two pairs of numbers, so it's functions on C star cross C star. But I'm not looking at the whole thing, I'm looking at a subspace, so I get this algebra mod some ideal. It turns out to be a principal ideal, meaning it's just generated by one thing. And this here is the A polynomial. Of course, after I take some normalization. Are there questions on that? I will say, if this thing seems like the most boring thing in the world, I will say kind of two intriguing facts. One, mathematicians, it can always be normalized so that the coefficients are integers. We don't have a categorification of it. Very mysterious. And the second thing is, when it first was made, people were really excited that it was a not invariant that had nothing to do with the Jones polynomial. And now we're very excited because we do think it actually determines the recursion relations of the colored Jones polynomial. So our sort of interest in this has swapped completely. Okay. So because of this second fun fact, that this is some quantization of this, has to do with recursion relations about some other not invariant that we love. We're going to quantize it. And the insight for quantization and now we're finally really at the stuff from my paper with David from this year, is that this this involves a defect, a topological defect. And why does that involve a defect? So I take one of the two knots that I can draw, evidently not under pressure. And I'm looking at its complement like this. And so the first step.
So I'm getting a bit
Yes,
lost.
yeah,
I mean, so what you said. So the last statement in the board on top is a lemma that says that the right hand side is equal to the left hand side. Or?
So this is something from like graduate algebraic geometry. So this part, it's just if you have some variety and you're looking at functions on a subset of that variety, you can write it as like a quotient like this.
Yes, but then why does the equivalent appear like that?
That is the definition.
Ah.
Yeah. Sorry. I will get my visa as a mathematician revoked,
So this
I
is
guess.
the definition of it, so it's the generator of that ideal.
Yeah. Yeah. So it's the generator of that ideal, and then you have to
With Z coefficients.
yeah, you can normalize, you have to pick some normalization, because the generator of the ideal is only defined up to an invertible element, so you have to do that. The other caveat is there's a lot of different conventions that I've swept under the rug behind this. If you're sort of interested, one thing is you could have some factor, this thing can factor, and a factor can show up with power 2 or 3, and it depends on what you're doing if you keep that multiplicity or not. Yeah, and it always has a factor of L-1, and some people throw this away and some people don't. But the main thing is that it has to do with, if you like flat connections, what it has to do with is you're looking at flat connections on the torus, which extend to a knot complement. And that defines for me like a Lagrangian in the character variety of the C-star character variety of the torus. I think physically it's connected to like the Hamiltonian of Chern-Simons theory. Maybe conjecture. Are there other questions? We're doing fine on time, so don't worry about. Okay, so, but this one step was I restricted to this Borel, right? But I only restricted at the boundary to the Borel, right? So I'm somehow in this situation where in the bulk, in most of my theory, I want SL to C going on, but at the boundary, I want T to C star, the maximal torus is C star here. And the big idea is that, well, this is an interface, in particular, it's some topological interface as you'd expect in a topological field theory, and it's associated to this Borel subgroup like this. So that's the one interface, and so that's what that does. So this was, what's nice about this is it both is restricting to the Borel, so I don't know if this cartoon is clear, but here what's going on is that I'm looking at a thickened torus with a sort of halfway point and some topological boundary labeled by B, like that. So this is kind of what's going on here. So in one fell swoop, I both do this restriction, and then after I do the restriction, I'm in my C star theory. And so from the boundary, I'm in this nice boundary theory here that I wanted to be in. And so the thought was, well, we needed to explain how to do skein theory with these surface defects. And in general, maybe so I'm not tempted to write less than I should. Let's change the grid. So I think the last 6 minutes, what I'll do is very briefly say how does this get implemented in skein theory, and then maybe what else do we want to do with it. Okay. So this is the story of topological defects. Okay, so right after I hinted we'd start talking about skein theory, the first thing I did is to find some category whose objects were graphs, ribbon graphs. And what I need to do now is I need to define that. But my category, it depended on this thing, repqg. Right? I had some algebraic data that defined what theory I was talking about. And so the first thing if I want to do defects is that I have to tell you what algebraic data determines my defect. So the algebraic data now, so let's say I have a theory defined by some category A. This would be a linear category, something like repqg. And another one defined by C, some other category. And I want to make a defect between them, some D like this. The data, it turns out, that I need to define that is, well, it will be a functor, because that's just the type of person I am. And what I'll do is I'll take some correct tensor product of these two categories. So this is a new category whose objects look like, an object here and an object here. And this drop means I'm going to do what's taking the braided opposite. For some sort of topological reasons. And I need a functor. I need to involve D here. D will also be a category. functor into D, but actually what I'll do is I'll land in the Drinfeld center of D. And what's the Drinfeld center of a category? This will be, the objects will be something D, some object in the category, and some data of how to take D, tensor anything, and swap the order at anything tensor D. So this thing is called a half grading. And I didn't think it would be of interest to this audience, so I could explain how these skein relations are built in some detail from this. But I'll just say the first part of it, which is what happens here. What I need to do is I need to make my definition rib sub D. And what is this going to have? Well, sort of I do the quickest thing I could do, which is I take my cylinder where all my graphs live and I just draw a defect in it. I just go like that. So this is going to be some stratified space. This will be a surface. And what I want for these graphs, on one side, I want it to look like this A theory, and on the other side, the C theory. So on the A side, I will just have graphs in the A theory. So they can have some topology. They're still oriented and framed and decorated, V1 and W1. And on the C side, the same, like this. But I want to have some interaction between these two theories. I don't want to just have two theories and an air gap between them. So what I need to do is I need to allow these skeins to pass through by defect also. So I need to allow them to pass through here. So this is our morphisms are like this. And just as before, my objects are going to be things like this. And a big part of so this is sort of an extremely rough definition of this thing. And a part of the theory was, or the work, was saying, well, what is the evaluation functor? And so we defined that. And you also need some functor to D, because I gave this functor and I used it to write some local relations down. So you do this, and maybe I could say how this is described like this. This is basically first one you project onto the defect. So I take all these curves, I just project them onto a planar thing, and then two, I evaluate using I'll call planar diagrammatics, which is just if I have a graph and a surface with the right data on it, I can grab a morphism out of there. Okay, so that was the story, and what it led us to do is take this stratified surface here and say if I take the skein module of this stratified thing, I will be able to present that in terms of some element in the skein algebra of the boundary, and that's my quantum A polynomial. So that's how that was done. I think I will say maybe out loud what needs to happen still. So one thing that's open is our main motivation for this was that this A polynomial is conjectured, AJ conjecture is conjectured to control recursion relations of some other invariant, and so we need to relate this whole thing with this skein module of some stratified space to actually the Jones polynomial. So that's one thing we need to do. And the other thing that we would like to do is to rewrite this theory for Lie superalgebras, which have more interesting parabolics. But the skein theory gets kind of much worse. Okay, I think I'll stop there.
So in this picture, Do I understand correctly that sort of this green plane is where the lines like that of the category D is supposed to live?
Yeah.
And why aren't there any such lines in this?
Oh yeah. Okay. So when we were writing down the theory, one because I was just drawing, I wanted to emphasize the two sides, but it turns out it depends on your particular application if you want to allow lines to be in the theory or not.
And
So
for the safe polynomial, you just don't want.
You don't want to. So yeah, and that was sort of for some like algebraic geometry reasons. Like it turns out if you take the theory and you you just only allow transverse crossings, and then you take the skein category of this thing and use that as your defect data.
Mhm.
That is like you're doing like an affinization procedure. So like the geometry will work out better. And we needed it to work out well. Okay, for us.
Does the construction give some kind of relation or additional insight into this hyperbolic geometry quantization of the A polynomial that you mentioned before?
Yeah, so one thing we realized is, so one of the, and we talked with Tudor regularly during this project, and one of the like most frustrating things for him in that project is that he doesn't have triangulation invariance. Like he needs an ideal triangulation, and for certain ideal triangulations of the knot complement, he just got like the wrong answer. Things would collapse, you would get 0. And so and we don't have that problem in this setting, and so we were sort of able to shed insight on like why that went wrong. It turned out there was just not quite enough framing data. Parabolic geometry couldn't do that. But we do think this like if you constrict it well enough, this will be a version of his. Yeah.
So you told the story about SL2 and this particular Borel. Is there hope to get other quantized knot invariants?
Yeah. So I mean, you could always this defect story, which I guess here I didn't write it at all.
That is very general, yeah.
Yeah, the defect story is very general, and it works for general parabolics. Just having that. The thing that breaks down is that you won't just have like this ideal being principal. This is like SL2. Like you would get like you still get like an ideal of polynomials, but you don't get just one.
Right,
Unless you have some way
makes
to
sense.
combine them together. No, but you would be interested in that. So these things, I was going on about how they quantize character stacks. But if you're studying local systems with essential singularities, this behavior, you end up needing to understand how these parabolic defects work very carefully to get a handle on like wild character varieties.
What are the defect data here?
Oh, how did we build ours, you mean? Yeah, so in general, the defect data is 2 bulk theories, so 2 ribbon categories, and 1 surface theory. All of this is like topological Yang-Mills setting, and that will be a pivotal category. So it's those 3 things plus a functor like this. So that's the data in general, and then how do we build that data? How did we build that data? Well, for us, it needed to be from rep QG, box tensor, rep QT, rated opposite, to the Strinfeld center of rep QB, like this. And we induced it from just, if I have B, this is a subset of G, and I can understand the maximal torus as a quotient. Like if you take your Borel and you make it abelian, right? Like you mod out by all the commutators, you get this. And so if this one is iota and this one is pi, our functor is roughly, you do iota star tensor pi star, like that. You can also do it if you, I think, more in line with people's interests. This will be like the invertibility of this defect is very subtle and interesting. You have to do some like localization. There's some like geometric stuff you have to do. If you just want like, if you have some action on G, you can, we don't know in what generality, but you could build one of these that would be like rep QG to rep QG again. So, for instance, the action of the val group gives you defects on just the rep QT theory.
Any final questions? If not, then let's stop Jennifer again.